a little bit of a problem with that. So let me explain the notation first. I already explained this notation, delta xk. Remember this delta xk notation, right? That's a small amount. It's not zero, but it's very small, right? Very small doesn't mean it's a zero. Then in the integral formula, there is this dx showing up in the integral, right? And what is the dx is trouble mathematicians because they have to give this logical foundation, and this is troubling them a lot. Right now, these days, they gave a correct foundation. It is long and complicated. I don't want to do that. So I will just look at it as a placeholder. The limit, change everything into single number, right? Riemann sum, it has a structure function part, delta x part, and xk part. All the components are there. If you take the limit, it becomes a single dull number. So notation of the integral kind of preserved where things are coming from, although it's representing a single number, right? So dx is indicating that there was delta x before, but whole symbol together you represent a single number. And we have the sigma notation there, right? K going from 1 to n in the Riemann sum, right? If you take the limit, they use this stretched s symbol from this sum notation that it was there before. So the notation, integral f of x dx, kind of keeps the structure of the Riemann sum before we take this limit in there, right? So when we analyze things, this is a proper notation, not a dx and f of x floating around. That is logical is not very good. So I tend to use this one. Book uses that, but engineering books and other physics book, they abuse the notation. They just simply use the dx. And for most function, there's no problem. You guessed the answer right. So what's the deal? But mathematicians care about this correct thing to use and a correct notation, and they tend to use that. So here's application. E to the sine x again. And let me pull up and this one and show you how to actually deal with this function. Here's a plot. This is going to plot the function. Sine x, you have to be capital like that. And x going from 0 to 2 pi. Maybe it's a trigonometric eventually. So if you go from 0 to 2 pi, it gives you the entire picture. So this is a function. And we were calculating integral of this one, right? Which was area underneath it, correct? Yeah. So I'm going to copy that. This is the function. Right, this is a function of y equals sine x, and this is between 0 and 2 pi. Make sense? So here's a question. I think this question makes sense because we are so exposed to this probability and statistics these days, every day. So if I choose a random number in here, x, and then you expect, okay, if I choose 2, there is this function value. What is it roughly in here? Maybe 2.25, somewhere there? Okay, so somebody asks you a question. If I just choose a random value in here, anything in between 0 and 2 pi, what is the expected value? If I choose this x equals 2, then this is the value. If I choose x equals 4, then is this value over here, and so on, right? But if I randomly, so 10,000 people participate and randomly choose this number, and then get the function value, and how do you actually get this expected value? Maybe we're going to sample all these 10,000 values here, and then we're going to collect all this function value there and average them out. That is the statistic definition, probabilistic definition of expected value. You sample very well distributed samples and take the average. Okay? So what I'm going to do is a wonderful problem because it's this notion that we think about every day has this complicated answer behind it. So that's my x1. Remember this thing, x1, and what is next one? x2. Those are my sample values, right? And then go in here, xn minus 1, and that's going to be xn. Correct? All right. So let's say it was well distributed. Everything is evenly, just not random distributed. So what is the expected value here? Expected value. Easier is what is the average, right, of this thing? That's what we're talking about. So what do? We add these f of x1, all the way up to where? F of xn, correct? Divided by n. There's n datas in there. That will be the answer. So you can actually sample 100,000 points and then get this value. So we want to be smart. So we write it like this: 1 over n. All right, this is sum notation. We learned this in like that, right? Soon as I write it like this, it looks a lot like Riemann sum. So we have to turn this one into Riemann sum. Riemann sum, general Riemann sum definition has xk star, but remember xk star is arbitrary choice. If it's a continuous function, no matter what xk star you choose, these will go to the same number eventually. So if you know it converges to common number, choosing your xk's, you're free. So xk star happened to be this xk. Is it right endpoint or left endpoint? Here's your xk minus 1, and there's your xk, right? So that's your right endpoint right there. That is my xk star. Hope it resembles that Riemann sum structure. Right, Riemann sum structure have one more thing in there, which is delta xk here, right? Delta xk is missing in that formulation. Is that right? So how would you calculate the delta xk in here? 2 pi is evenly divided into n pieces, right? So right endpoint is a 2 pi, and left endpoint is a 0. If this were 1, not 0, then 2 pi minus 1 will be the length of it, right? Is that okay? And you're going to divide this one by what number to get this interval in here? N. There are n pieces, right? Think about, play with it. N equals 5, and you can use it. So right endpoint minus left endpoint is the length of interval. Divided by number of intervals in there, n. That's going to be what value? Delta xk. Right, we want that up here right there. Then you can turn that into integral, correct? So I'm going to do that. Well, this manipulation, some people you like that manipulation, but if not, you can turn that formula, and knowing that n appeared there, can you solve this one for n so that I can replace that n with this formula, and then it's going to be integral, right? So can you solve this for n? Is it delta xk divided by 2 pi? Is that right? Right. So you can put that 1 over n inside. So k going from 1 through n, f of xk, 1 over n. This 1 over n can go outside the summation because 1 over n does not change as k varies. As k varies, this changes, then you can't go, put it outside the sum like that. So you can put it inside because it's independent of k. And what would we, do you have a question? Yes. Thanks for the correction. I was thinking wrong. So it's 2 pi over delta xk. It's corrected. So that one becomes now k going from 1 through n, f of xk, times 1 over n, it would be 1 over 2 pi divided by delta xk. Is that okay? That's how you turn that. All right. Then 2 pi is a constant. You can pull that outside. Is that right? So it's 1 over 2 pi. An integral from k1 through n of f of xk times, because it's reciprocal, delta xk is in the right place. Okay? Do you recognize this is a Riemann sum? Right, if there are lots of points, then this, we can't exactly compute this one. We don't even know what those x1, x2 are, but we know if n is really, really large, this is going to tend to what value? 1 over 2 pi is a constant multiple there, right? And what happened to that part right there? Limit. What happened to the sigma notation? Sigma changes to stretched integral symbol, right? F of xk changes to just f of x. And that delta xk changes to dx, right? And this is definite integral. You got to put the numbers around here. What is the number? Starting from 0, that's how it started, and ending at 2 pi. Correct? So if there are 10,000 and 10 to the 1,000th power number spread apart, and this is expected value. Okay?
So you just replaced 2 pi with the 10 to the 1000. That's the only change in the problem for that one.
No, that is happening over here. N being some large number, for example, 10 to the, like this. Are you thinking about this one here? Yeah, but this is some number, but I am claiming that if the size of a number is like this number, we can't really calculate, is awfully close to that number, which is 1 over 2 pi integral. Okay? So the problem is this f of x and interval 0 to 2 pi, that 0 to 2 pi showed up here, right? And this representing average. Where does 2 pi come from? 2 pi came from b minus a. Remember? This right endpoint of the interval we're looking at is 2 pi. Left endpoint of interval was 0. That's where that came from. B minus a divided by number of intervals. That's where a number of intervals disappears. It goes inside to this delta x part. So in general, if I'm looking at function f of x and randomly choosing a point in between the point a to b, your expected value is this one in here. So the general formula is the following. 1 over b minus a, those are the length of interval down there, and going from a to b, f of t dt. What does that represent? Expected value of f of x on interval a to b, right? If you have to gamble with this f of x, that's the one that you have to go for, like 100 times. But there you have a good chance that you will hit the right number. All right. So the point is that, so what is it? You did all that mumbo jumbo things. What is the value? This is not something you can calculate exactly. So you have to numerically integrate. So the function for that is n integrate in Mathematica. So exp and sine x there, and x from 0 to 2 pi. And if you do that, it's going to calculate at 7.95. It is ranging, I forgot to divide it by 1 over 2 pi. That's why it's so often. This is ranging only in between 2.5. The expected value being 7.95 is wrong, right? So you have to divide it by 2 pi in there. You have to put the parenthesis. So it's 1.266 is the expected value for this function. All right? I think it's really, you don't have to enter any complicated physics problem to get an application of this Riemann sum. It's a very simple example that sophisticated idea is behind this thinking about average problem. In fact,